we are asked to give the molecular geometry of the molecule shown. Now the first step in determining the molecular geometry is to determine the number of electron groups. The way to do that is to first draw the Lewis structure. Now we're going to tally up the electrons present in this molecule in order to give us a better idea of what the Lewis structure will look like. Xenon has 8 electrons, 2 oxygens which have 6 electrons each, and there's 2 fluorines which have 7 electrons each. This totals to 34 electrons. Now the Lewis structure looks something like this. Now you're going to notice that you're going to have 2 leftover electrons. You just have to know that xenon can actually break octet. You would put the lone pair on xenon. And it's important to notice here that there is 4 bonding pairs of electrons as well as 1 lone pair of electrons, totaling up to a total of 5 electron groups. Now this is key into telling us which molecular geometry we're going to apply. For molecules with 5 electron groups present, there is 4 different structures of molecular geometry that can be used. In this case, we're going to be using the one that has 4 bonding pairs and 1 lone pair. The shape that corresponds to our molecule is the distorted tetrahedron, also known as the seesaw. I'll show a picture later to show where it gets the name, the seesaw. We start off by drawing the first 3 atoms that are on the same plane. In this case, we're going to use xenon, which is the central atom, fluorine, and oxygen. Now notice that these lines are not straight. That's because this is not 180 degrees. There's actually a lone pair over here that causes repulsion that bends the molecule away from the lone pair. Now, the reason for this is that lone pair, bonding pair, repulsion is stronger than bonding pair, repulsion. Now what that means in simple terms is that the repulsion between these fluorines and oxygens is actually going to be weaker than the repulsion that those fluorines and oxygens experience from the lone pair on the xenon. Now we're just going to finish distributing our electrons. One of these, in this case the oxygen, is coming towards us. Fluorine is going away, so we're using the wedge. There are 3 angles that are significant to us in this structure. The first one's over here. And now normally if this was just a trigonal bipyramidal structure which has 5 electron groups, none of them being lone pairs, this would be 180 degrees. Because of what we talked about, that the lone pair repulsion is actually stronger, this angle is actually going to be greater than 180 degrees. I'll indicate that with this. This angle here is also known as axial. It's going to be, normally would be 90 degrees in the structure of the trigonal bipyramidal, but in our case this is actually going to be less than 90 degrees. This angle here is called the equatorial. This is also going to be less than 120 degree of its counterpart, trigonal bipyramidal, which has no lone pairs present. This is a program generated image of the molecule that we just drew, which is probably a lot more clear. I just wanted to show the rationale behind the way we draw it. You can see the same angles here. This is going to be greater than 180. This is our xenon here. It doesn't matter which one's which. We are fluorine or oxygen, or fluorine or oxygen. This is our axial angle, which we discussed is less than 90 degrees. And this is our equatorial angle, which which is less than 120 degrees. This is another perspective on the same molecule, which is showing the atomic orbitals and the orbital overlap. Now, unfortunately, this program doesn't have the capability to show us the lone pairs. So the lone pair that will be here is not shown. This is also appears to be 180 degrees, which is inaccurate because, like I said, it doesn't include the lone pair bend. So this would be greater than 180. This looks like it would be. This is a model kit representation of our same molecule. Xenon would be here. Oxygen and fluorine, like I said, doesn't matter where we draw these. This is our lone pair. You can actually see very clearly where this molecule gets its name, the seesaw. We can very easily have a person here riding the seesaw, a person here on the floor, and you can see how the seesaw action would happen. This last slide is the same molecule that we showed in the previous slide. I just wanted to show this perspective because it differentiates between the axial versus equatorial. It's very important to understand the difference between these. If we were to remove another atom and have a secondary lone pair, we would never remove from the axial locations. You cannot remove these, you would just remove an additional equatorial, which would give us a T-shaped trigonal bipyramidal structure, which corresponds to one less lone pair. Now again, this model kit doesn't show us the greater repulsion of a lone pair bonding pair when compared to the bonding pair repulsion. So this appears to be 90 degrees when it's actually supposed to be less than 90 degrees. This appears to be 120 degrees when it's actually supposed to be less than 100. This is where the 180 degree angle would normally be, but again, because of the bend of this lone pair, this would actually be greater than 180 degrees.